are going to have a look at the fluorite and anti-fluorite structure. And this assumes very important is the fact that most structures carry this type of structures. There are a lot of atoms that will show you where to. Just a minute, I'm not going to. There are many such crystals. They are classified into fluorite and anti-fluorite crystals. So here the motif is, the motif is a para. I mean that a design or a structure that is very common, or a template you should call it. So we have seen them in the form of MX2 type. So for compounds of AX2 type, like for example calcium fluoride, in which the radius ratio Ra exceeds 0.73. So I think you have in the beginning itself you have seen how the radius ratio is influencing the structure. We have seen how the CCP is cubic close packing, when you get key CCP, when you get BCC, and when you get TD, like that, based on the value of this radius ratio. So if the radius ratio exceeds this value of 0.73, the fluid structure mat may be adopted. With this structure, calcium plus ions are arranged at the corner and face centers of a cubic unit cell. So we assume this as a cubic unit cell. Here you can see that I put the structure there. So this is the cubic unit cell that is mentioned there. So I'm just you must draw this, otherwise we don't give full marks to students who do not draw this. Drawing is very essential. Okay. So that is the cubic cell, and you can see that at the corners it is mentioning about the corner. So where do we have these corners? Corners and face centers. So these are the corners there. Okay, you can see these are the corners there. And we consider one thing as a face. This is a particular face. Okay, so this happens to be a face, and the center of a face, particular face, we call this as the face center. Okay, that is mentioned there. So face centers of a cubic unit cell. The two fluorine atoms motifs. I think motif, I told you, it's a template or a design or a structure. Template is better for you to understand. At 141414 is the coordination that is shared by the atoms. Suppose if you take this particular atom, you can put one more cube here, and another cube here, another cube here. That is at the back side, right? The back side. So this one, this one, this one, this one. So you got 4 different possibilities of connecting this. See, if you can see this, imagine this particular atom there, and this atom is shared by how many cubes? This cube, okay, and then this cube, second one, and then this one, third one, and then this one, fourth one. This is third one, and this is the fourth one there. So 1, 2, 3, and 4. These 4 cubes are shared by that. So each particular atom is shared with 4 atoms. That is what is meant there. Now minus 1 by 4 means it is opposite of that. So this is, if you consider this one, all the top will be, you just put it as plus, all the bottom you will just put it as minus. That is what mentioned. For each lattice point, each calcium plus 2 is surrounded by 8 F minus cations. So let us see how it is surrounded by 8. So let us take this calcium atom there. Okay, so where have we that calcium atom is here, and you can see it is surrounded by 8 fluorine atoms. 1, 2, 3, and 4. So likewise, you have got this at the bottom. 6, 4, 5, 5, 6, 7 and 8. Okay, so that is how it is shared. It's an important point that you mentioned the uh, calcium atom is surrounded by 8 F atoms. I think it's a very important point there. 8 F minus. So these 8, you can just see how they are plotted there. You can even join them together like this, right? So that forms another cube there, another rectangle there, right? So that forms a cube within the cube, but the arrangement is different. If you look at this particular face, which I have drawn the blue face here, then calcium atoms occupy the corners. The two faces. The center of the faces is having one more calcium atom, but apart from that, just some distance from there, you will have one atom that is fluoride. So likewise, just some distance from there, you will have an atom that is fluoride. So likewise, from here you will have an atom that is fluoride. Likewise, from here you will have an atom that is fluoride. So how many fluoride atoms you will have? You got 1, 2, 3, 4 at the bottom fluoride atoms, bottom 4 and top 4. So you got 8 fluorine atoms and one calcium atom at the center. And then these things will keep on repeating for that. So that you can imagine here. So you can see that this is here it is mentioned about metal and oxide. You can just take it as a calcium and fluoride there. So this will be at the corner in calcium, and then the fluoride atoms are arranged at a distance just from these calcium atoms here. So here only one unit is shown. This is a very general structure. I think in this tip you forget about this diagram. I wanted to mention the plus and minus signs there. Why it is there. So here it will be better. And each F atom is surrounded by 4 Ca2 plus. So you can see that uh, calcium atom is surrounded by 8 fluorine atoms, and each fluorine atom, suppose if this is your fluorine atom, it is surrounded by 1 and 2 and 3 and 3 and 4. So these 4 are the calcium atoms there. So that is mentioned there. The Ca2 plus is actually, this is the Ca2 plus at the corners of a tetrahedron. So you need to recall how we mentioned the corners of a tetrahedron. That means, if I can just superpose the structure there for that drawing a tetrahedron. If I draw like this, okay. So one atom I will be putting here, another one here, leave this, and here, leave this, and here. Okay, so if I have a center there, I can connect to 4 atoms like this, 4 different corners. So this forms a very good tetrahedron there. Okay, so a tetrahedron is formed as a result of that. So that is being mentioned there. This leaves alternate cubic interstices vacants and results in the octahedral cleavage of fluorite and isostructural minerals. Isostructural minerals means minerals of the same structure. The cubic coordination of F about a central is the result of a radius ratio of RCA with RF. That is, the radius of calcium divided by radius of fluorine is approximately 0.75. If it is just less than that, it will be occupying only a pure cubic close packing. But because it is greater, you have to put in more some coordinates there. These cubic coordinations, polyhedral shares edges only. So again, I am going to tell you what the edges are. These are the edges there. So this is an edge. This is an edge. This is a corner. Okay. So this is also an edge. This is also an edge. So there are a lot of edges and corners. And this blue square which I have drawn here, this blue square is the face. So you should remember face, corners and edges, three things always to be able to write about that. So in short, the most important point is that you must remember the radius ratio of calcium to fluoride or in a fluorite structure. This is a basic structure should be approximately 0.75. These cubic coordination polyhedral share edges only. Similarly, tetrahedral arrangement of tetrahedral coordination of polyhedral share only edges. This arrangement allows for maximum separation of the Ca2 plus ions, cations from each other. So this is a very good arrangement. Because of this, cation has double the charge of the anion. The number of anions in the structure must be double that of the cations in the order to achieve electrostatic neutrality. So what it is telling is, you have Cu2 plus, you should have sufficient F minus. So each Cu2 plus is to be balanced by these minus and minus charges. That is how you will maintain the electrical neutrality. So a structure that you should write about the calcium fluoride is this one. Here you can see that this is the calcium there, and this is the fluoride there. Now they are all occupying the corners. So how many of them are there? 1, 2, 3, 4, 5, 6, 7, and at the back, at the back of this here you'll be having 8 if you go from this, or if you go from this. So these two lane will take you to another fluoride, another calcium structure there like this. So this will be the 8th one. And apart from this, you'll have the center part, that is the 9, 10, 11, 12. Here at this back 13 and below that 14. So 8 corners, you'll have 8 corners of calcium will be occupied by 8 corners, and how many faces? 6 faces. So in all, you will have 14 atoms there as a result. And then within that, from each calcium, there will be, at a distance of about 2 or 3 angstrom units, there will be fluoride structure. So likewise, you can have a fluoride structure like this particular place. Fluoride. This is also fluoride. And likewise, you can also have another fluoride structure there. And likewise, you can have another fluoride structure there. So this will be giving you another cube like this. It will go. So it can keep on going. And you must count that each calcium is having one fluorine atom, and it is surrounded by 4 fluorine atoms. So 1, 2, 3 and 4 at the top, 5, 6, 7 and 8 at the bottom. So within a particular cubic cell you are having calcium, 14 calcium and 8 fluoride atoms. Okay. So but that doesn't mean that it is not similarly balanced. I told you that in the beginning that not all the fluorine atoms are bonded together, not all the calcium fluorides are bonded. It's just a packing structure. The real bonding will be between one calcium and one fluorine there and another fluorine here. So you will have only CaF2 structure there. But the packing goes on in such a way that you will have one more F here and one more F here. Okay, so this goes on packing like that. So it tends to give you a structure which you can just better write it like this one in the beginning. Okay, this is a very good structure. So you have to draw this structure again to 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 give the importance that I am just drawing the structure again here. You can draw 4 cubes. This one. So here it is. So I'm just joining them. So if I join them, I can even draw a structure like this. Right? So after drawing, you get four cubes like this. After drawing this, you can place the atoms there. What are that calcium atoms? I'm just placing at the corners. Then at the one face is there and corners are there. Okay, so I'm just putting the top layer only, and then you can see what I mentioned. I'm just going to put one fluorine atom there. Okay, and this is connected to this fluorine atom is connected to another calcium also, because this happen to be at the corners of a regular tetrahedron. You will have another calcium there, and this will be connected by this, and then you are having another calcium atom here, and this will be connected to this. So only two will be bonds there. What are the two bonds? This will be the bond and this will be the bond, and this will just be the arrangement. These two will be the arrangements. But you can see that the bonds that I have put, and I'm just going to highlight this bond, this bond, this bond, and this bond. They just go to corners of a tetrahedron. That is how you have to draw it. So similar such things, you just have to draw it, and then you will get a fluoride structure for that. Okay, so how is the fluoride structure finally fed? Now I'm just going to show you the difference between the fluoride and the anti-fluoride structure. Uh, the anti-fluoride structure is geometrically identical with the fluoride structure, right? Just you can see that the anti-fluoride structure is anti-fluoride is geometrically identical, but but the positions of positive and negative ions are, but the positions of positive and negative ions are interchanged. So you can just see what is happening in the anti-fluoride structure. For example, in the case of Li2s, Li2s, Na2s, K2s, and rubidium 2s, these have the anti-fluoride structure. These have anti-fluoride structure. You must mention it. This is a very important point there. The structure corresponds to the, again, this is corresponding to the structure of the binary type MX2, or we just call it as the AB2 type, where you have the sulfur atoms. The sulfur atoms are occupying the CCP arrangement, cubic closed packing, and according to FCC, face centered cubic arrangement. You can see that. So what has happened here? This is the fluoride structure. This is the anti-fluoride structure. So just you can see that the sizes are the same, and the positions is being different. I mean, that is the cation and anion things are changed, and here the coordination for M is 0, 0, 0, right? This is the coordination. 0, comma 0, comma 0 there. But the coordination, that is the starting point, is half the way between this, so that is why you just put it half. So you start from here in this case, but you start from here for the fluoride case. So this is a structure that is giving you the enough things to occupy when there is a change in the cationic size. So let us look into the structure of that again. I'm just going to import another structure there. Each metal atom is surrounded by 4 sulfur atoms tetrahedrally. So here is that, this one, anti-fluorite structure. This is the case of MgSi4, I think Mg2 plus Si4 minus. Each metal atom is surrounded by a metal atom. That is, the magnesium is surrounded by 4 silicon atoms, and each silicon atom is surrounded by 8 metal atoms. So again, you can just concentrate on this, how this one, this is magnesium. Magnesium is surrounded by how many? 1, 2, 3, and 4. But if you consider this as the silicon, how many it will be surrounded? 1, 2, 3, 4. 4 at the bottom and 4 at the top. That is why you will have 8. So we can write magnesium surrounded by 4 silicon, silicon surrounded by 8 magnesium. This is the main point about this fluid structure. Therefore, the coordination, the coordination will be 4:8, or roughly 1:2. And this structure is similar to zinc blend. But in zinc blend, half of the tetrahedral sites are vacant. So this is the main difference between them. I think I can just put you the anti-fluorite structure also again. Or you can just mention this thing. So if I have a picture of this anti-fluoride structure and fluoride structure combined, that will be the best thing to visualize. So this, I think I have already imported. This you have to draw. Okay. And the anti-fluoride structure in a very detailed manner I am just putting again. Yes, coming back again, the same thing. Oh, that is the anti-fluoride structure. Here it is. You can see how quite similar to this one is to this one. While you can just see another example, you can just take up another example, like for example, sulfur. What is taken? Lithium, sulfur. Okay. Then you can see the tetrahedral elements. This is quite similar to this one. This is quite similar to this one, and all the yellow atoms are the metals, and then this will be the sulfides. The sulfur atom is surrounded by 8 metal atoms. You can just see how 8 metal atoms are there for this sulfur. So you consider this as sulfur 1, 2, 3, and 4 in a particular layer is there. Okay, likewise the bottom you have 1, 2, 3, 4. So 4, 5, 6, 8 surrounding is there. So it is only talks about the surrounding pattern. Okay. So in short, I'm just summing it up. The calcium fluoride structure has a stoichiometry of type AB2, and if it crosses the radius ratio divided by 0.5, we are going to have the simple cubic structure getting converted into the calcium fluoride structure. It is not only confined to calcium fluoride, it is there for so many such atoms there. So for that you have to draw the diagram that I have shown at the beginning. And then in the anti-fluorite structure, the next important point is you just say geometrically it is identical with the fluoride structure, but the positions of positive and negative ions are interchanged. So you can draw the similar diagram, a very quick same diagram, but and just change the cations and anions as shown here, or the best diagram to describe in one go is this will be this one. The origin will be from here and the origin will be from there, cation and anion. And origin means that basically it changes the entire pattern of the structure. Similar geometrical structure, similar Q, similar packing, but how the ions are placed and where the ions are started is a different thing. Obviously, here at the beginning you will have two atoms there. It is quite different from the one when you start from this one. So this is the best structure that can describe you the fluoride and anti-fluoride structure. Okay. So if you have any doubts, you can just have a look at the notes in the description section. I have given the points there in the description section. You can just see there and come back to me if you have any doubts. Thank you for joining.